Hi, I'm Kade Bowers.
And I'm Matilde Garcia, and this is lab number 8, and it's interference by division of amplitude.
This is a Michelson interferometer. So how this works is we have a mercury lamp set up as our source, which goes through here, and then we have a beam splitter right here. What happens is that half the light by division of amplitude gets reflected to mirror 1, half the light gets reflected to mirror 2. The important thing, this is a corrector plate, and we have that because when it gets reflected to mirror 1, it goes through the beam splitter 3 times, but going this way it only hits the beam splitter once before coming back out. So this corrects for the path length.
Here we have the circular fringes, also known as the Haidinger fringes, that we found using the interferometer. To find the circular fringes, the tip or tilt of mirror 1 and mirror 2 had to be the same, but the optical path difference had to be different because if they were equal, we would just see one big fringe.
The optical path difference is the distance between A1 and A2. As the optical path difference decreases, we can see that the interference lines will actually go towards the center, contracting. Also, since we are viewing this from this plane reference, we can see that the fringes will get smaller and closer together as the optical path difference decreases.
For this section, we found straight line fringes, which are also known as fringes of equal thickness. To get the fringes of equal thickness, we have to have the mirrors at the same optical path distance relative to each other, and then we tilt them relative to one another. So it doesn't matter so much how the micrometer moves mirror 2 translationally, but it matters that they're aligned with each other and the optical path difference. And as we decrease the tilt of the mirrors relative to each other, it increases the fringe spacing. So vice versa, as we increase the tilt relative to each other, it decreases the fringe spacing. To find our white light fringes, we started from our straight line fringes and we replaced our mercury source with a white light source, and then we put a red spatial filter over it. What that red spatial filter allowed us to do was to find the fringes for just the red light, and then we took that away, and then we found when the fringes appeared for the white light fringes. This corresponds to an optical path difference of 0, so that you can see all the wavelengths.
In the pattern of white light fringes, we see black fringes destructively interfering and white constructively interfering. In places between the black and white, we see partial interference, and in between them, one can see the rainbow pattern. As you diverge from the initial white light, the wavelengths go out of phase with each other.